Hi, I'm Maciej. I'm a software engineer. In my previous video, I have shown you a couple of very useful functions which I have implemented to support video processing in Mathematica. These were waveforms and vector scope. It's very interesting to see that in the new version of Mathematica, these two utilities will be available as standard functions. And this shows how Mathematica is, how much it's expansive as a computing platform. It's more and more difficult to find a computable domain which wouldn't be completely covered or at least supported. Of course, I don't regret implementing these functions myself. They work exactly the way I wanted, and it also allowed me to bite the problem of implementing such functions for video processing. It also allowed me to gather some thoughts and do some experimentations related to performance optimizations. The reason why performance was critical in implementing these functions is that every single video frame contains 8 million pixels, and there are tens of such frames in a second, and there are 60 seconds in a minute, so even for a short movie we are talking about billions, if not trillions of mathematical operations to process them. I will show you why the proper use of language idioms is particularly important in such cases. Okay, so this is Mathematica again, and to demonstrate my point, I will create an array of random integers. These are integers from 0 to 10. And I will also just take a very short sample from the very beginning of this array so that we can see the results of some computations. So here it is. And let's suppose that my computational problem is how to multiply every number in this array by 10. So let's suppose that I'm a C or C++ programmer, and I would like to repeat the idiom that I know from the C programming language. I would do it something like this. I would prepare the place for result, so that would be also an array of 10 elements, and I would write a simple for loop that will scan the array of numbers from the beginning to the end, and that will compute the results for every index of the array. These are my results. You can imagine that this is something that a C or C++ programmer would attempt to do in Mathematica. I can also imagine that a programmer coming from a functional programming language perspective would write something like this. He would define a function that simply multiplies its argument by 10, and he would map the function over an array. So the results are the same. There is another syntax for this which can be useful in some situations. It's really the same operation. It's just a more funny way of writing the same. There is another way of doing something similar. Instead of defining a function, a named function, for performing the operation that we are interested in, we could also define the anonymous function and map this operation over the array. We can expect the same results again. As you can see, this functional way of writing programs is much shorter, and some programmers consider it to be more natural or more convenient. However, you might find it interesting that the most natural way of implementing this operation in Mathematica is simply multiplying the whole vector by the number we want to multiply. This is what happens. It might be surprising to C or C++ programmers because this operation doesn't make any sense in those languages. It can be also surprising to Python programmers. I will show you why. Here's my terminal for a while, and this is the Python console. In Python, when I multiply an array by 10, what I get is I get a 10 times longer array with all the elements repeated. So this is just a repeated concatenation of the same array. In Mathematica, however, such an operation is said to be listable, which means that it's applied for every element of an array if one of the operands happens to be an array. So this is really the shortest way to write the operation that I wanted to perform. So what is the performance of these three different approaches, or actually four? Let's find out. So this is my C or C++ style of writing again, but this time applied to the long array of 10 million elements. I will not show the result of this operation. This semicolon will suppress the output, and I will measure the time it takes to execute this operation. As you can see, it took almost 19 seconds to execute. I have skipped that part of the video. You really wouldn't like to wait that long. So almost 19 seconds. So let's see how it will perform for the functional application. Almost 7 seconds. It's a lot faster. The fans of functional programming would say that this is really a proof that functional programming is much better than the imperative one, which is practiced in C. But let's see what happens next. So here I'm measuring the functional application again, but with the anonymous function. As you can see, it's a lot faster now, which means that there is something interesting happening inside Mathematica. We can find some analogies with the application of a compiled expression, like here. What happens here is Mathematica is taking the expression that I provided and internally compiling it for the virtual machine that is executing the simplified version of this code. So now what happens is that we get a very similar result. This indicates that Mathematica can internally compile the anonymous function when it's applied in the functional style. It didn't do this when the function was separately defined and named. But what is really surprising is this result. It's still a lot faster. It's actually 1,000 times faster than the C style implementation, which I have attempted at the very beginning, or which the C or C++ programmer would do, because this is exactly the style of C or C++. So what really happened here? Actually, Mathematica has many of these operations optimized internally, and it simply executed the internal procedure for doing exactly this operation. The difference in performance is 1,000 times. What it means is that it would be very bad for me to implement such operations in the C or C++ style, like here. It wouldn't be also very wise of me to implement this in the functional style, even though the result is much better. What I should really do is I should implement it in the style that is the most natural for the tool that I'm using. And in Mathematica, the most natural style of doing this operation is simply by benefiting from the listability of operations. So 10 times a vector is simply a vector of numbers multiplied by 10. This is the fastest way of executing this function. As you have seen, the proper use of language idioms is very important. We need to code and think in the same programming language. We need to learn the language idioms inside out and use the ones which are the most relevant for the particular language of our choice. And don't think that if you are efficient in one programming language, which you might know very well, you will be automatically efficient in another language. This is not true. I'm Maciej, I'm a software engineer. Thank you very much for watching this and see you next time. By the way, it is also possible to do something like this. Here what I'm doing, let's call it my C function. What I have done here is I have provided my implementation in the Wolfram language. This is the C style of implementing such an operation. And I have told Mathematica to compile this function by generating a C code for this algorithm. So now I can call my function, which operates on the array of integers. I can call it and I can see that it executed a lot faster than the initial implementation. It doesn't mean that this became a good Mathematica idiom. No, it's still a bad Mathematica idiom. It only shows that this is the C-style programming, which can be adopted in Mathematica as plan B when the natural idioms are not enough. But these techniques should be really applied only when the good idioms are exhausted and do not provide the required functionality. See you next time.